Hi guys, welcome back to Data Every Day. Today we are looking at a data set of graduate school admissions. So we have different students, their GRE score, their SOP score, and their cumulative GPA, and then whether they were admitted or not. And it's a very simple data set, only 4 columns, but we're going to do a little EDA and then a little, we're going to train a logistic regression model on the data to try to predict admittance based on the scores. So let's hop into the notebook. I'm importing NumPy and pandas for working with the data, and then these are all for visualization. We have pyplot, seaborn, plotly graph objects, and we're just getting this function make subplots from plotly.subplots. Then for actually training, we're using these to prepare the data. We're going to use stratified k-fold to evaluate the data since we have using very few rows in this data set. And the standard scalar just for standardizing the columns of the data set. Then we'll use a logistic regression model to make our predictions. So I'll go ahead and import that, and we can load in the data using pandas.readcsv. I'll just make this a little bigger, and we can get the file path up here, admission predict.csv, and I'll paste that in, and we can take a look. So it is very simple, only 400 rows and 4 columns. It's more of a beginner data set. So I figured we can do some exploratory data analysis. Nothing crazy, just want to visualize some of the aspects of the data. So here we can see there are no missing values. Additionally, there are no object columns, but that is obvious by looking at it. And then I guess we'll just get right into the EDA. So let's look at data.describe. Just have like a little text EDA. You can see the min and max of each value. So it says here that the GRE scores are out of 340, SOP scores are out of 5, and CGPA scores are out of 5. However, when we look over here at the maximums, we get 340, 5, and 10. So GPAs are actually out of 10. We have to keep that in mind. The means are all fairly high. I mean, this is pretty standard, 3.4 for, yeah, I mean, the means do seem to be on the high side, especially the GRE. We have 316. But let's do this. What I want to do is create a radar plot. I'm sure you've seen them before. They're like, look like spider webs. And we're going to show the mean GRE score, SOP score, and CGPA score for both admitted and non-admitted students. We'll see if there's sort of a larger spread on the admitted students. So we're going to use plotly graph objects for this. I'm creating a new plotly figure here using the make subplots function. So we're going to create a subplot figure and then put in the traces to each subplot. And I'm going to only show 2. I'm going to show one plot for the students who were not admitted and 1 plot for the students that were admitted. So we'll have 1 row and 2 columns. And we're going to specify the number, the type of each plot. So we want to make sure that the type is polar for both subplots. Because we're showing a polar charts. And then I'm just going to give them some titles. I should probably put this in there in its own lines here. We're going to give subplot titles will be not admitted and admitted. Alright, so now what we'll do is add the traces in. So I want to show the means for both the admitted and non-admitted students. So what I'm going to do, if we have data, I can query the data to just get the admitted students with .query, checking wherever admitted equals 1. Now we'll just have the admitted equals 1 students. So what I'll do is I'll call data 0, that'll be the non-admitted students, and data 1 will be the admitted students. And these will come from data.query, admitted equals, and then this one will be 0, and this one will be 1. So now we have 2 sections of the data, I'm going to add a trace for each one. So fig.addTrace. And we're going to add a scatter polar from plotly graph objects. So go.scatterPolar. That's just a polar scatter plot essentially, and we will fill it in so it looks like that radar chart. Then we specify an r and theta values since it's a polar plot. The r value is going to be the actual values that we're getting. So these are the means. The mean of each column for data 0 is what we're looking for here. So we're going to do data 0 sub GRE dot mean, and then we'll display data 0 sub SOP dot mean, and then we'll show data 0 sub CGPA dot mean. However, these are on different scales as we saw, and if we graph it this way, we'll have the GREs will completely take over the scale of the plot because the GREs are on a scale up to 340, whereas these are up to 5 or 10. So we want to scale them all. We can scale them by the maximum values found in the original data to give them values between 0 and 1. So we'll do not data 0, just data sub GRE dot max. So if we divide by the max, we're effectively scaling between 0 and 1. And then GRE here is going to be SOP, and this is going to be CGPA. Alright, so the theta here is just going to be the names of the different points around the plot. So we have GRE, SOP, and CGPA. Alright, then we'll include a fill, doing toSelf fill, and then the name, this is going to be the not admitted graph. Alright, and then we'll just specify which row and column we're using, so row 1, column 1. And let's show it. Equals, forgot the equals up here. Oh, did I not import this? Make subplots. No, it doesn't make sense. Oh, I wrote subplots. Okay. Alright, and here it is. So we haven't done the admitted one yet, but you can see they're all on the same scale between 0 and 1, where 1 is the maximum value found in the original data. So you can see that the GREs, the mean GRE is quite high, whereas these ones are not as high. Now we're going to do the admitted. So I'm just going to copy this over here. Actually, this whole thing. We're going to add another trace, this time in row 1, column 2. And this is the admitted data. This all stays the same. All this I have to do is change these to 1. And now we should be able to see we have admitted and not admitted. And it does look like we have some higher SOPs and higher CGPAs than we do over here. So it makes sense that we're seeing higher grades on the admitted students. I guess I'll just give this a title as well. We can do that with fig.updateLayout. Title text equals student performance. Okay. Alright, so now I'd like to get some correlations. So I'm going to assume the correlations for this data are pretty high because we're going to expect to see as the grades go up, the other grades go up, and as the grades go up, the admission goes up. So let's get a correlation matrix with data.core, and we can display it with Seaborn's heat map. I'm going to pass in core. Actually, let me specify the figure size first using pyplot. So we'll give it a figure size of 12 by 10. And I'm turning on annotations here so we can see the actual Pearson correlation coefficients. And then the minimum value is going to be -1, and we'll give it a color map of Mako. Alright, and I'll give it a title. This will just be confusion matrix. And we'll show it. No, sorry, it's not confusion, it's correlation. My bad. Alright. And there we go. So, yeah, very high correlations all around. Nothing crazy, but you can see, especially in the admitted column, as the GRE goes up, admitted is going up. As SOP goes up, admitted is going up. and as CGPA goes up, admitted is going up. So there's a direct positive correlation between all of the columns here, which is exactly what I expected to see. Alright, now let's do training. So, because we have such few data points, let me look at data again. We only have 400 rows. So if I split it into a test set, we're essentially really limiting the amount of data the model is seeing. And so it is probably not the best idea to use a test set evaluation to evaluate the performance of the model. Now, the other way to get a sense of how the model's doing, especially is useful when you have few rows, is with k-fold evaluation. K-fold cross-validation. In this case, we're going to be using stratified k-fold cross-validation, which just means that each fold is going to have roughly the same class distribution as the original data. And so what I'd like to do is first split this into x and y. So y is going to be the admitted column. That's what we're trying to predict. I'll make a copy as well. And then x is going to be everything except admitted. So we're dropping it from axis 1 and making a copy. And now what we'll do is create our training loop. So I'm going to train k different models, where k can be any number. You can either pick 5 or 10. We'll try it with both. So what I'm going to do is create this results list. It's just an empty list that I'm going to append things to later. And then we're going to create our stratified k-fold object. So k-fold, if you're not aware, basically divides the data up into k different sets, and then uses one of those sets as the test set and the other sets as the train set. And it does this k times, where each time the test set becomes a new one of these sets. And so each time you do this, it's known as a fold. So we specify the number of sets we're using with n splits. We'll start with 5. And then what I'm doing is for train index and test index in skf.split xy. Explain this. skf.split, the split function looks at x, looks at y, calculates the class distributions using y, and then splits x into 5 different sections based on how many splits we have, where the class distribution is similar. And then it gives us the indices for the train set and the indices for the test set for each of our 5 splits. So we're doing this iterating for each of the splits, and each time we get a set of train indices and a set of test indices. And then what I'll do is with these train indices and test indices, I'll create my x train, y train, x test, and y test. And so the x train and x test are, well, let me do them one at a time. X train is going to be x sub, well, I'll do .loc actually. We're going to use all columns, but the row indexer is going to be given by train index. And I might as well make a copy so that we're not changing the original x. And then, very similarly, the x test is going to be that, except with test index instead. Now the y train is just going to be y sub, I can do loc again, I guess. Well, let me do iloc for index location. And then y.iloc train index dot copy. So this is going to be just the train set y's, the train set x's, the test set x's, and this will be the test set y's given by y.iloc test index dot copy. Alright, now we have our 4 sets of data for a given split, and now we will scale the data using a standard scalar. So a standard scalar will just give each column a similar range of values. The standard scalar in particular will give each column a mean of 0 and a variance of 1. And we can fit the scalar to our x train. We don't want to scale our y, since that's the target we're trying to predict. And then we're going to transform both x train and x test using our fit to the train set. And we do this because we want to sort of pretend we don't have access to the test set at the time of fitting the model. So we're going to use scalar.transform. Here is xtrain, and this one will be xtest. And this will return the transformed version of the set we pass in. However, it does return it as a NumPy array, and because we're messing with indices here, it's important that we return it back into a data frame so that we can refer to the correct indices in the right way. So pandas.dataframe, keeping the indices as they were before. So the top will be xtrain.index, the bottom will be xtest.index, but I also want to keep the columns the same just in case we want to look at it again. So xtrain.columns. And now here is xtest, and here is xtest. Alright, now we've scaled the data, and we're going to fit the model. So our model will be logistic regression. We'll train a new model for each iteration, and we'll fit it to xtrain, ytrain. And then when we're done, we're not going to print anything out. In fact, we're going to append the result to our results list. So results.append model.score xtest, ytest. So in the case of a classification model like the logistic regression model, the score function will return an accuracy value. So we're evaluating the model on the test set, this set of data, and then we're going to store that result in results. Alright, and that's it. Let's run that. So now our results should be filled up with accuracy values, and we can say for I in range, I'll say this. Let me make this markdown and say results. For I in range length of results, so for each result essentially indexed by I, we're going to print out the fold number. So we'll say fold number, and then we'll show the accuracy value. We'll display it to 2 decimal places, and we'll give it a %, and then format it with results sub I, the ith result, and then multiply it by 100 since we're looking at a percentage here. We actually also have to put in the index here, which is just I plus 1. I'm doing plus 1 since I want fold 1 instead of fold 0 at the beginning. And then once we've printed out all those the accuracy value for each split, I want to get the average accuracy across all splits. So I'll say average test accuracy, and we'll display this to 2 decimal places, again with a %, and format that with numpy.mean of results. And let's multiply that by 100 as well. Alright, and here is the result. So you can see some splits have a really low accuracy, some splits have a higher accuracy, and then the average split, the average test accuracy is sort of a good measure of how the model's doing, how the model would do if fit on the whole data set. So this keeps you from having to use a test set. If you're using a very small number of rows, taking a test set would not be so beneficial because you might be losing out on valuable data. So this is a nice way to evaluate the model in case you don't have that many rows. So let's bump up the splits to 10. We should get a similar thing. We just have 10 accuracy values, and it looks like our test accuracy is about the same. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.